How do you check the health of steel that spent 20 years at 600 degrees, without cutting a single sample? With a piece of plastic film and a microscope. This is replica metallography. Why look at microstructure at all? Because long before a component fails catastrophically, the material tells you it's degrading, if you know where to look. Replica metallography gives you a non-destructive window, remaining life assessment, creep damage monitoring, and inspection without removing a single sample. The component never leaves service. The method is 8 disciplined steps. First, surface preparation, clean down to bare metal. Then grinding, to remove the mechanically disturbed layer. Then polishing, and yes, you can get a mirror finish in the field. Etching comes next, a few seconds of chemical attack reveals the grain structure underneath. Now the clever part, a softened acetate film is pressed onto that etched surface. It flows into every microscopic detail and hardens into a perfect negative. Peel it off, and the replica carries the microstructure back to the laboratory. Under the optical microscope, at up to 1,000 times magnification, you read the material like a book. And step 8 is the one that matters most, engineering assessment of what you found. Before hunting defects, know the baseline. This is healthy austenitic steel. Equiaxed grains, all roughly the same size. Clean, thin grain boundaries. And fine carbides, small, rounded, evenly dispersed. Notice what's not here, no voids on the boundaries, no continuous films, no cracks. Every defect in this video is a departure from this picture, so fix it in your memory. Grain structure isn't academic, it controls everything. Fine grains mean higher strength, through the Hall-Petch relationship. Grain size affects toughness, and therefore resistance to brittle fracture. Boundaries govern creep resistance, they're where diffusion happens. And boundaries deflect cracks, so they shape how cracks propagate. Read the grains, and you read the material's future. Now the first finding, carbide formation. At service temperature, carbon diffuses through the steel and concentrates at the grain boundaries. There it meets chromium and forms M23C6 carbides, you can see them as dark particles decorating the boundaries. The price is sensitization, the zones beside the boundaries are drained of chromium and lose their corrosion resistance. Keep running hot, and the carbides evolve. Early in service they're fine and dispersed. With long-term exposure, the small ones dissolve and feed the big ones, Ostwald ripening. The end state is coarse, widely spaced carbides, and the strengthening they provided is gone. The carbides are the steel's temperature diary, and this is what a long, hot chapter looks like. Grain growth is even more direct. These 3 fields are the same magnification, count the grains. Fine and healthy on the left, larger in the middle, a warning, and very coarse on the right. When grains grow 5 or 10 times, the steel has been overheated. Strength drops. Toughness drops. Now the big one for high-temperature plant, creep. It starts invisibly, isolated cavities nucleating on the grain boundaries. Then the cavities grow, fed by stress and temperature. They multiply and start to link up, coalescence, aligned perpendicular to the stress direction. And the final step, the chains become microcracks. This entire sequence is readable on a replica, no other field technique sees it. Look closer. Each dark dot is a cavity, roughly a micron across, sitting exactly on a grain boundary. They nucleate where diffusion and stress combine, and they orient perpendicular to the loading direction, which is why experienced inspectors can tell you the stress state from the cavity pattern. Small as they are, these voids are the earliest warning you will ever get. When coalescence goes far enough, microcracks form. They initiate at boundary triple points, grow along the boundaries, and link into networks. At this stage the damage is no longer theoretical, remaining life is short, and the finding drives a formal assessment. This is exactly why the earlier stages matter, catch it at cavities, and you never see this picture. Cracks tell their story by the path they take. On the left, intergranular, the crack weaves along the grain boundaries, avoiding the grains themselves. That's the signature of creep, stress corrosion, or sensitization-assisted attack. On the right, transgranular, the crack cut straight through the grains as if they weren't there. That's fatigue, or overload. Same steel, same microscope, completely different mechanisms, and completely different responses. Temperature attacks chemistry as well as structure. In chromium steels held between roughly 600 and 900 degrees, sigma phase forms, hard, brittle islands where cracks love to start. At the surface, oxidation builds an outer scale while oxidation penetrates along the boundaries inside. And beneath the scale, decarburization strips carbon from the steel, a soft, weak layer with reduced fatigue strength. All three are visible on a single replica. Put it together and you get the full arc healthy material. Creep cavities. Micro cracks. A macro crack. And finally, rupture. Damage accumulates with time, and every stage before the last one is detectable with a replica. That's the entire business case. You can watch the clock, instead of hearing the bang. So what do you do with each finding? Fine carbides, low severity, monitor on the normal interval. Coarse carbides and grain growth, moderate, increase the inspection frequency and evaluate remaining life. Creep cavities, high, they trigger an API 579 fitness for service assessment. Microcracks, also high, detailed NDT sizing. And intergranular cracks, critical, repair or replace. Defined findings, defined responses. Why replicas instead of cutting samples? Sectioning metallography is destructive, the component comes out of service, costs more, and gives you one examination, one time. Replica metallography leaves the component in service, costs less, and, most importantly, is repeatable. You can examine the same spot, year after year, and watch trends. Sectioning is for failure analysis after the fact. Replicas are for monitoring, before the fact. And this is how it closes the loop. Inspection produces a replica, the replica reveals the microstructure identifies the damage feeds an API 579 fitness for service assessment, the assessment estimates remaining life, and remaining life drives the decision, monitor, repair, or replace. Evidence-based, documented, and defensible. That's the difference between inspecting and engineering. The takeaways. Replica metallography detects early degradation, in service, without cutting. Microstructural changes appear long before failure. Creep cavities and microcracks are the critical indicators. And combined with API 579, replicas turn maintenance into engineering. Healthy on the left, end of life on the right, know which one you're looking at. Thanks for watching.